Hello students, welcome to this lecture on three-dimensional geometry. In this lecture, we will cover NCERT section 11.3, 11.4 and then we will solve NCERT example 6 to 8. So let's get started. This is disclaimer. So first we will study equation of a line in space. So there we will know equation of a line through a given point and parallel to a given vector. Then in section 11.4 we will discuss angle between two lines. Then we will solve NCERT examples 6, 7 and 8. So I hope you are ready with your notebooks and pens. So let's start today's first topic 11.3 equation of a line in space. So line in 2D. A line is uniquely determined either by its slope and a single point or by two distinct points. Okay. To uniquely define a straight line in 3D, we also need two key pieces of information just like in 2D, but the specifiers are a bit different. So let's look at what those are. Okay. So the first thing we need is a specific point through which the line passes. So this point gives us the position of the line in space. The second thing we need is the direction of the line. This tells us the path of line follows in space. So let's start by looking at the vector form of a straight line in three-dimensional geometry. So let the line passes through a point A with position vector A and be parallel to a vector B. Now let's introduce the position vector R for a general point P on the line. This means that R represents the location of any point P that lies somewhere along our line, not just at point P. Here is a diagram to help you visualize the situation. So look at this diagram very carefully and try to visualize what we are want to say. So let's focus on the vector form A to P, which we call AP. So mathematically AP equals R vector minus A vector. Since R vector is the position vector of point P and A vector is the position vector of A. So R vector equals vector A plus vector AP using a vector addition. Since the line is parallel to vector B, the vector AP must also be parallel to B. That means we can write AP as lambda times vector B, where lambda is a scalar parameter that can take any real value. Now let's substitute AP vector as lambda times B vector into our earlier equation, and then we get vector R equals vector R minus vector A equals lambda times vector B. Finally, rearranging the equation gives us the vector equation of the line, that is R vector equals vector A plus lambda times vector B, where lambda is any real number, that is called scalar. Now let's look at an important remark about direction ratios in three-dimensional geometry. So we will see how a vector can represent the direction of a line and what the components of the vector mean. Suppose we have a vector b written as b equals b1 I cap plus b2 j cap plus b3 k cap. Here b1, b2 and b3 are the components of the vector along the x, y and z axis. The numbers b1, b2 and b3 are called the direction ratios of the line. If you already know the direction ratios of a line which are b1, b2 and b3, so you can use them to write a vector that points in the same direction as the line. So if b1, b2 and b3 are the direction ratios, then the vector b equals b1 I cap plus b2 j cap plus b3 k cap will be the parallel to the line. So now let's start by looking at the Cartesian form in three-dimensional geometry. Suppose point A has coordinates x1, y1 and z1 and the direction ratios of our vector B are b1, b2 and b3. Then we can express it as r vector equals x times I cap plus y times j cap plus z times k cap, where x, y and z are the coordinates of any general point on the line. Okay, and I, j and k are the unit vectors along the axis x, y and z. So this is written as vector A equals x1 I cap plus y1 j cap plus z1 k cap. Here x1, y1 and z1 are the coordinates of point A, and again I, j and k are the unit vectors. So we have vector B equals b1 I cap plus b2 j cap plus b3 k cap. The values b1, b2 and b3 are the direction ratios which tell us the direction in which the line extends from point A. Now let's substitute these expression into the vector equation of a line. So the general vector equation is r vector equals a vector plus lambda times b vector. So we often, after substituting, we get the equation x I cap plus y j cap plus z k cap equals x1 I cap plus y1 j cap plus z1 k cap plus lambda times b1 I cap plus b2 j cap plus b3 k cap. Finally, by equating the coefficients of I, j and k on both sides, we can separate this vector equation into three scalar equations. So see here, the equation x equals x1 plus lambda times b1, where x1 is the x coordinate of a point on the line, b1 is the direction ratio along the x-axis, and the lambda is a parameter. The equation is y equals y1 plus lambda times b2, where y1 is the y coordinate of the point on the line and b2 is the direction ratio along the y-axis, and solving for lambda gives us lambda equals y minus y1 divided by b2. Similarly, let's write the equation for z. So z equals z1 plus lambda times b3, and by solving lambda we get lambda equals z minus z1 divided by b3. where z1 is the z coordinate of the point on the line and b3 is the direction ratio along the z axis. Since lambda is the same in all three equations, so we can set the expression equal to each other. So this leads us to the symmetric form of the line, which combines all three coordinates into a single equation. So therefore we get the symmetric form x minus x1 divided by b1 equals y minus y1 divided by b2 equals z minus z1 divided by b3 equals lambda. So this is the Cartesian form of a line through a given point and parallel to a given vector. Now let's look at an important note in three-dimensional geometry. So here L, M and N represent the direction cosines of the line, which tell us the direction of the line along the x, y and z axis. So the point x1, y1 and z1. So x1, y1, z1 is a specific point that the line passes through. So then the equation of the line is x minus x1 divided by L equal y minus y1 divided by M equals z minus z1 divided by N. Okay, so this is called the symmetric form of the equation of a straight line in three-dimensional geometry. Now we are asked to find both the vector equation and the Cartesian equation of a line that passes through the point 5, 2, minus 4 and is parallel to the vector 3i cap plus 2j cap plus minus 8k cap. Okay, so first of all, think about this. How would you approach this example and then see solution? So let's start the solution step by step. So given that vector A equals 5i cap plus 2j cap minus 4k cap and vector B equals 3i cap plus 2j cap minus 8k cap. We know that if a line passes through a point with position vector A and is parallel to a vector B, then we can use these directly in the equation of the line. So this is the standard result in vector geometry. So the general vector equation of a line is r vector equals vector A plus lambda times vector B, where vector r represents the position vector of any point on the line. Now let's substitute our given vectors into this formula to get the specific equation for our line. So now the vector equation of the line is vector r equals 5i cap plus 2j cap minus 4k cap plus lambda times 3i cap plus 2j cap minus 8k cap. Okay, so this is the vector equation of the line passes through the point 5, 2, minus 4 and is parallel to the vector 3i cap plus 2j cap minus 8k cap. Now let's define vector r as the position vector of any point P with coordinates x, y, z that lies on the line. So therefore xi cap plus yj cap plus zk cap equals 5i cap plus 2j cap minus 4k cap plus lambda times 3i cap plus 2j cap minus 8k cap. So now let's expand this equation to group the I cap, j cap and k cap components together. So we get xi cap plus yj cap plus zk cap equals 5 plus 3 lambda I cap plus 2 plus 2 lambda I j cap plus minus 4 minus 8 lambda k cap. Now let's move on to the Cartesian form of the line. So now we are going to find Cartesian equation of the line through the point 5, 2, minus 4, and which is parallel to the vector 3i cap plus 2j cap minus 8k cap. The general Cartesian equation of a line passes through the point x1, y1, z1 and is parallel to the vector b1i cap plus b2j cap plus b3k cap is x minus x1 divided by b1 equals y minus y1 divided by b2 equals z minus z1 divided by b3. Here the vector A is equals x1 I cap plus y1 j cap plus z1 k cap and vector B equals b1 I cap plus b2 j cap plus b3 k cap. Therefore, substituting our values into the formula, we get the Cartesian equation for the line is x minus 5 divided by 3 equals y minus 2 divided by 2 equals z plus 4 divided by minus 8. So I hope this example is clear to all of you. Now we will discuss now equation of a line when 2 points are given to us. Okay, so now we are going to know equation of a line of 2-point form. So first of all, we will discuss vector form of a line. So let's consider a line passing through 2 points, point A with position vector A and the second point is B and its position vector is B. Let's introduce vector R, which represents the position vector of any general point on the line. So the direction of the line is given by the vector AB, which is B vector minus A vector. Now using the point direction form, we write the equation as vector R equals vector A plus lambda times direction vector. Here lambda is a parameter that can take any real value and it helps us generate all points along the line. Therefore, the complete vector equation of the line is vector R equals vector A plus lambda times vector B minus vector A. Okay, so this is the vector equation of a line in 2-point form. Now let's start by looking at the equation of a line in 3-dimensional geometry in 2-point form for Cartesian form. Okay, so now we will discuss equation of a line in Cartesian form. Suppose we have 2 points A and B with coordinates A as x1, y1, z1 and B as x2, y2, z2. Now let's consider any general point on the line which we will call is x, y, z. To do this, we need the direction ratios of the line. So these are simply the differences between the coordinates of B and A. So A equals x2 minus x1, B equals y2 minus y1 and C equals z2 minus z1. Now let's recall the general Cartesian form of a line in 3D. Okay, so we know the Cartesian form of a line is x minus x1 divided by A equals y minus y1 divided by B equals Z minus Z1 divided by C, where A, B and C are direction ratios. Now, on substituting the values of A, B, C from earlier, we get the specific equation for a line passing through 2 points given by x minus x1 divided by x2 minus x1 equals y minus y1 divided by y2 minus y1 equals z minus z1 divided by z2 minus z1. So this is the 2-point form of the line in Cartesian form. Now we will start by understanding the main idea, the angle between two lines in 3-dimensional geometry. Okay, so the angle between two lines is defined as the angle between their direction vectors. So look at the figure in figure 11.4. okay, so now let's look at the equations for the two lines. The first line is L1 and the equation is vector r equals vector a1 plus lambda times vector b1, and the second line is L2 equals L2 such that vector r equals vector a2 plus mu times vector b2. Here r is the position vector and a1 vector and a2 are the points on each line, and lambda and mu are the parameters, and b1 and b2 are the direction vectors for each line. Then the angle theta between two lines is simply the angle between the direction vectors b1 and b2. Now to find the angle, we use the dot product formula for vectors. So b1 dot product b2 equals magnitude of b1 times magnitude of b2 times cos theta. So if theta is the acute angle between the two lines, so we want to find a way to calculate this angle using vectors. So then cos theta equals modulus of b1 dot product b2 divided by modulus of b1 vector times magnitude of b2 vectors. It's important to note that we use the absolute value in this formula to make sure we always find the acute angle theta, not the obtuse one. Now we are starting with the Cartesian form in 3-dimensional geometry. So here we define the direction ratios for two lines L1 and L2. For L1, the direction ratios are A1, B1 and C1, and for L2, they are A2, B2 and C2. And the image shown helps you visualize these lines and their orientation in 3D space. Now let's write the direction vector for line L1. It is B1 vector equals A1 I cap plus B1 J cap plus C1 K cap, where I cap, J cap and K cap are unit vectors along the X, Y and Z axis. Similarly, the direction vector for line L2 is B2 vectors equals A2 I cap plus B2 J cap plus C2 K cap. Similarly, I cap, J cap and K cap are unit vectors along X, Y and Z axis. Next, we calculate the dot product, that is B1 vector dot product B2 vector equals A1 times A2 plus B1 times B2 plus C1 times C2. Now let's look at the magnitudes of the direction vectors. The magnitude of B1 is square root of A1 square plus B1 square plus C1 square, and magnitude of B2 is square root of A2 square plus B2 square plus C2 square. Finally, we substitute the dot product and the magnitudes into the formula for the cosine of the angle between the lines. The equation is cos theta equals the absolute value of b1 dot b2 divided by product of magnitudes of b1 and b2. So if theta is the acute angle between the lines, then cos theta equals absolute value of a1 times a2 plus b1 times b2 plus c1 times c2 divided by square root of a1 square plus b1 square plus c1 square times square root of a2 square plus b2 square plus a2 square, where a1, b1 and c1 are the direction ratios for the first line L1 and a2, b2 and c2 are the direction ratios for the second line L2. Now we are starting our discussion on special cases in 3D lines. Let's begin by defining perpendicular lines in 3D. So two lines are perpendicular if the angle between them is 90 degrees. This is just like in 2D. But now we are considering lines in space, not just on a flat surface. To analyze perpendicularity in 3D, we use the vector form. So for direction vectors, b1 and b2, these vectors show the direction each line points in space. So we will use this to check if the lines are perpendicular. The formula to find the angle between two vectors is cos theta equals absolute value of b1 dot b2 divided by magnitude of b1 times magnitude of b2. Since we are talking about perpendicular lines, so the angle theta is 90 degrees. So cosine of 90 degree is 0. So our formula simplifies. That means the numerator b1 dot b2 must be 0. So the key condition is b1 dot b2 equals 0. If the dot product of the two direction vectors is 0, then the lines are perpendicular. So two lines in 3D are perpendicular if and only if the dot product of their direction vectors is 0. Now let's look at the special cases. Okay, another special cases. So for direction ratios a1, b1, c1 and a2, b2, c2, cos theta equals absolute value of a1 times a2 plus b1 times b2 plus c1 times c2 divided by square root of a1 square plus b1 square plus c1 square times square root of a2 square plus b2 square plus c2 square. We know that cos theta equals cos 90 degrees, which is 0. So for the lines to be perpendicular, the numerator of our formula must be 0. That means a1 times a2 plus b1 times b2 plus c1 times c2 equals 0. So two lines with the direction ratios a1, b1 and c1 and a2, b2 and c2 are perpendicular if and only if a1 times a2 plus b1 times b2 plus c1 times c2 equals 0. Now we will see another case in 3D lines. So let's define parallel lines in 3 dimensions. When two lines are parallel, the angle between them is 0 degrees. That means they point in exactly the same direction, never meet, no matter how far they extend. So in vector form, the condition, if two vectors point in the exact same direction, one must be a multiple of the other. Therefore, for theta equal to 0 degree, the vector form condition for parallel line is b1 equals k times b2, where k is greater than 0. Here k must be positive because the angle is exactly 0 degree, meaning they are in the same direction. If k is negative, it would imply theta is 180 degrees. So two lines with direction vectors b1 and b2 are parallel if and only if b1 equals k times b2. Now we will see this condition in condition form. So let's define the direction vectors of the first line. We write it as b1 equals a1 I cap plus b1 j cap plus c1 k cap. Here a1, b1 and c1 are the components of the direction vectors along the x, y and z axis, and I cap, j cap and k cap are the unit vectors in those directions. Let the direction vector of the second line be b2 equals a2 I cap plus b2 j cap plus c2 k cap. Now the numbers a1, b1, c1 are the called the direction ratios of the first line, and a2, b2 and c2 are the called direction ratios of the second line. Now let's apply the vector condition b1 equals k times b2. This means that the direction vector of the first line is a scalar multiple of the direction vector of the second line. So if b1 equals k times b2, then each component of b1 must be proportional to the corresponding component of b2. In other words, a1 must be k times a2, b1 must be k times b2 and c1 must be k times c2. So a1 equals k times a2, b1 equals k times b2 and c1 equals k times c2. From these equations, we can solve for the value of k. This means we can write k as a1 divided by a2, k as b1 divided by b2 and k as c1 divided by c2. Let's see here. So k equals a1 divided by a2, k equals b1 divided by b2 and k equals c1 divided by c2. Since all the direction ratios are equal to the same scalar k, so the condition for parallel lines when the angle between them theta is 0 degrees can be written as a set of equal ratios. That means a1 divided by a2 equals b1 divided by b2 equals c1 divided by c2. This equation tells us that for two lines to be parallel in 3D, the ratio of their A components and B components and C components must all be equal. So two lines with direction ratios A1, B1, C1 and A2, B2 and C2 are parallel if and only if A1 divided by A2 equals B1 divided by B2 equals C1 divided by C2. Now let's look at an example. In this example, we have to find the angle between the pair of lines given by vector r equals 3 I cap plus 2j cap minus 4k cap plus lambda times I cap plus 2j cap plus 2k cap, and vector r equals 5I cap minus 2j cap plus mu times 3I cap plus 2j cap plus 6k cap. So first of all, try it yourself and then see solution. So let's see how to approach this example step by step. To start, remember that the standard form for the equation of a line in vector notation is vector r equals vector a plus lambda times vector b. Now on comparing, vector r equals 3I cap plus 2j cap minus 4k cap plus lambda times I cap plus 2j cap plus 2k cap, and vector r equals 5I cap minus 2j cap plus mu times 3I cap plus 2j cap plus 6k cap with the standard form, we get here b1 vector equals I cap plus 2j cap plus 2k cap, b2 vector equals 3 I cap plus 2 j cap plus 6 k cap. Now finding out the magnitudes for b1 vector and b2 vector. So magnitude of b1 is square root of 1 square plus 2 square plus 2 square, and magnitude of vector b equals square root of 3 square plus 2 square plus 6 square. Now the angle theta between the two lines is given by cos theta equals absolute value of b1 dot b2 divided by magnitude of b1 times magnitude of b2. This is equal to absolute value of I cap plus 2 j cap plus 2 k cap dot product 3 I cap plus 2 j cap plus 6 k cap divided by square root of 1 plus 4 plus 4 square root of times square root of 9 plus 4 plus 36. This is equal to absolute value of 3 plus 4 plus 12 divided by 3 to 7 equals 19 divided by 21. Hence, theta equals cos inverse of 19 divided by 21. So the angle between the given two lines is theta equals cos inverse of 19 by 21. Now let's look at example 8. In this example, we have to find the angle between the pair of lines x plus 3 upon 3 equals y minus 1 divided by 5 equals z plus 3 upon 4, and x plus 1 divided by 1 equals y minus 4 divided by 1 equals z minus 5 divided by 2. So first of all, try it yourself and then see solution. Let's start the solution. So we know the standard Cartesian form of a line is x minus x1 divided by a equals y minus y1 divided by b equals z minus z1 divided by c, where a, b, c are the direction ratios of the line. On comparing, x plus 3 upon 3 equals y minus 1 divided by 5 equals z plus 3 divided by 4, and x plus 1 divided by 1 equals y minus 4 divided by 1 equals z minus 5 divided by 2 with the standard form. The direction ratios of first line are 3, 5 and 4, and the direction ratios of the second line are 1, 1, 2. If theta is the angle between the lines with the direction ratios 3, 5, 4 and 1, 1, 2, then cos theta equals absolute value of 3 times 1 plus 5 times 1 plus 4 times 2 divided by square root of 3 square plus 5 square plus 4 square times square root of 1 square plus 1 square plus 2 square. This is equal to 16 divided by square root of 50 times square root of 6 equals 16 divided by 5 times root 2 times root 6, which is equal to 8 times root 3 divided by 15. Hence, the required angle is cos inverse of 8 times root 3 divided by 15. So I hope this example is clear to all of you and you are getting my point. That's all for today's lecture, and thank you for your attention. I hope this lesson was helpful to all of you.